I would like to teach some math in a curious historical context. There's a man named William Morgan. He lived in New York in the 1820s and joined a secret society with the intent of discovering and publishing their secrets. Some in the society realized his intent and decided to be rid of him. Though his body was never found, one within the group confessed of involvement in the disappearance before his own death. About 70 years later, a character based on William Morgan appeared in the 1895 sci-fi novel Etadorpa. The character, only known as I Am the Man, a play on the name William Morgan, is sentenced by the society to be exiled to live within the interior of a hollow earth. Before you laugh at the plausibility, consider the following. There have been very large, deep-focus earthquakes as far below the planet's surface as 440 miles, with aftershocks as distant as 20 miles away. Yet there is no reasonable mechanism to explain this. The demands of Newtonian physics at depths of just 45 miles below the surface require temperature and pressure to turn rock from something that fractures into something that is ductile and flows. The deep quakes have the seismic wave characteristics of shear quakes, yet there should be nothing at these depths to shear. There might be further evidence that there are specifically defined regions where Newtonian mechanics don't apply, these all being geometrically defined below planetary surfaces. For nearly a century, geophysicists have based seismic wave calculations for the crustal region on the existence of something called the Conrad discontinuity, believed to underlie all continents at a level between 6.2 to 9.3 miles. The discontinuity marked what seismologists thought was a transition from an upper, less dense layer of granite to a denser layer of basalt below. This region has been postulated because a downward traveling seismic wave will speed up from 3.8 to 4 miles an hour at the discontinuity. On the Kola Peninsula in northwest Russia, scientists chose to drill the deepest borehole in the world. There, geophysicists calculated the Conrad to be at a depth of 4.3 miles. Counter to the implications of Newtonian gravity, the density of the granite never changed. A basaltic layer was never found. They kept encountering a brittle, constant density granite to the depth of 7.5 miles. At 7.5 miles, the coring drill hit a granite that had become glass-like and impervious to further exploration. This happened at the same depth at 3 other holes. At this point, they felt that at this much deeper depth, the position where the granite transitioned from brittle to strong must be the Conrad discontinuity. While there are a few places on some continents where the Conrad discontinuity doesn't appear to exist, it's generally pervasive. However, Germans, French, and Americans have attempted lesser drill holes than the Kola, all in the attempt to find wave-refracting structures and fail to find what they're looking for. The Conrad is said to be the boundary between the upper crust and the lower crust. Between the lower crust and the mantle, scientists surmise a second major discontinuity called the Moho, another region where seismic waves are supposed to undergo a substantial change in their velocity. The Moho varies in depth also, from 10 miles under low-lying plains or 10 miles under ocean bottoms, down to as much as 35 miles under the highest mountain ranges. We've already seen that the Conrad discontinuity can't be found where predicted, so the values of the Moho might also be questioned. As mentioned, at the Kola drill site, rock density did not increase with depth, as would be predicted by Newtonian physics, nor did temperature or atmospheric pressure behave in a predictable way. In the novel Etadorpa, rocks have constant density as one descends into the earth. Overlapping fields that start at about 10 miles below the Earth's surface are responsible for the supposed wave change velocities that we may incorrectly interpolate. The field may be two separate fields, mocking the effects of the Conrad and the Moho, Or it may be a single field with varying thickness spanning a portion of the region between the Conrad and the Moho. In this book Etidorpa, there's a second set of overlaps at about 700 miles below the Earth's surface, a region called the Sphere of Energy, or the Sphere of Gravity. Between these overlaps, Newton's laws don't apply, being said to be a subset of a more encompassing set of rules. There are 9 regular polyhedra, just as there are or were 9 planets, 5 terrestrial and 4 gaseous. I submit that nearly the entire weight of the Earth is due to an invisible gravitational field, a field that scientists may one day realize is a form of dark matter, a field that is formed by invisible geometric solids that pair up in very peculiar ways. There's another more distant historical thread upon which this narrative hinges. From the 6th century BC to the 1st century AD, Greek philosophical speculation paved the path that led to modern science. The watermark for the start of modern science is arguably Johannes Kepler and his 3 laws, the most important of which is that the planets move in elliptical paths with the sun at one focus. This law enabled Newton to think clearly about the balance between a planet's attraction to the sun and the planet's momentum of motion in its path around the sun. Kepler was far from being modern. He just wanted to prove his Neoplatonic speculations to be true. Before we address the nature of those speculations, we need to examine a few of the Greek precepts that led to Kepler's breakthrough. In the 6th century BC, Anaximenes asserted that the planets and fixed stars are attached to invisible crystalline spheres, and these crystalline spheres moved around a spherical Earth-centered universe. Contemporary to Anaximenes, Pythagoras and his followers left us with more than one influential thought. Their studies in ratio, music, and astronomy spawned a cohesive philosophy. Not only did they contemplate the musical tones that the planets might emit, they created musical instruments and healed themselves by diet and dance. The more wisdom and asceticism they sought, the better their chances of a favorable reincarnation. However, they too were a secret society, failing to dedicate their ideas to written form, so we can't be sure which of their influences progressed as the golden age of Greek thought unfolded. Before I mention the next chronological character in this puzzle, I need to clarify some terminology. There is a difference between a polygon and a polyhedron. If I say hexagon, I mean a flat, 6-sided figure. If I say regular hexagon, I mean a flat, 6-sided figure where all the edges and angles are equal in measure. If I say hexahedron, I mean a 6-sided, 3-dimensional solid. If I say a regular hexahedron, I'm talking about a perfect cube. If I mention an octagon, I'm referring to a flat, 8-sided figure. If I mention a regular octagon, I'm talking about a flat, 8-sided figure that has identical edges and identical angles. When I speak of a regular octahedron, this refers to an 8-sided solid with all the faces being identical. While the suffix hedron, singular, or hedra, plural, designate 3-dimensional solids, the prefix tetra indicates 4 faces, octa, 8, dodeca, 12, and icosa means 20. As a contrast, I introduced 2 other polyhedra that are important to the subject matter. The rhombic dodecahedron has 12 identical faces, but it's not a regular dodecahedron. It's not regular because there are 2 different angles represented on each face. The second of these polyhedra is the rhombic triacontahedron, which has 30 rhombi. Once again, this figure is disqualified from being called regular because each rhombus has 2 different angles per face. Anyway, 2 centuries after Pythagoras, a man arrives on the Grecian scene that does commit ideas to writing. Plato compiles and expands upon the Starry Night universe that went before. Using the geometry of the 5 perfect solids, the tetrahedron, 4-sided, the octahedron, 8-sided, the icosahedron, 20-sided, the cube or hexahedron, 6-sided, and the dodecahedron, 12-sided, Plato proposes the underlying forms for all matter. In this starry night universe, the Earth sits at the center of the universe, and all the visible stars, excluding the planets, are embedded on something like a sphere of fixed stars. Unlike today, when we know Betelgeuse and Vega are known to be different distances from us, Plato thought that all non-planets were nearly equidistant from us, and they were said to be embroidered by the Creator not on a sphere of fixed stars, but on a dodecahedron, a dodec once again centered on the Earth. Plato's Creator, or demiurge, exists in a world of being, a world of perfect forms or archetypes. The demiurge transitions into the receptacle of space, the world of becoming, and takes all the chaotic forms and refines them, reducing or increasing their measures in order to correspond in some proportion to the archetypes back in the world of being. These archetypes are thought by most to simply be the 4-sided, 8-sided, 20-sided, and 6-sided figures previously mentioned. Others think that a true archetype is like a subcomponent of the equilateral triangular faces, a 30, 60, 90 triangle, for instance. Most, however, believe that the tetrahedron, octahedron, icosahedron, and cube are the archetypes Plato was concerned with, and that these forms account for the various forms of fire, air, water, and earth. The entire creation, from fixed stars to the central Earth, constitutes the world body, which has a world soul. Unlike Anaximenes, who supplied invisible crystalline spheres to explain the movements of the planets, Plato's demiurge gave godlike properties to the planets. After all, the planets move, so they must have some form of life. The creative powers that the planets absorb become supreme in the realm of becoming, as the demiurge retires to the world of archetypes, or the world of being. In his musings, Plato suggested that planetary orbits must be explained by mechanisms that demonstrate uniform circular motion. Such a thought became dogma for several generations thereafter, until uniform and circular became two separate ideas. In the 3rd century BC work of Apollonius, circle centers are no longer centered on the Earth. As Apollonius attempted to explain the orbit of the Sun around the Earth, for example, Apollonius adopted an imaginary point D from which the motion would appear uniform. The Earth is really at point T. The lowercase e is the apparent distance that the imaginary point D is from the Earth. Sometimes the Sun is as far from the Earth as r plus e, sometimes as close as r minus e. By the 2nd century AD, Claudius Ptolemy refined and compiled the astronomical speculations of the Greeks. In the large eccentric circle at the left, the big central dot is the Earth. It is not at the circle center C. Uniform motion for the center of the smaller circle F occurs with respect to point Q. The point P, P for planet, on the outside circle then has a uniform circular motion around point F. The uniform motion may vary in its period depending on what heavenly body you're trying to describe. While this is a simplified version, such mechanisms do a fair job of predicting planetary positions. The path that these mechanisms attempt to describe are represented in the diagram on the right. The Earth is assumed to be in the center. The Sun's path is a tiny circle next to the center. One level up and overlapping the tiny circle is a cardioid that maps a circuit of Mars. The single small loop at the top of the cardioid, the loop that overlaps the Sun's circle, is a representation of the apparent motion of Mars as it moves backward and then again forward from the Earth's point of view. The outer floral pattern represents one circuit of Jupiter against the background of the zodiac. While the left-hand diagram just looks like circles to us, Ptolemy thought of some of these circular mechanisms as invisible crystalline spheres of varying thickness. As he attempted to calculate the distance to the outermost sphere, the sphere of fixed stars, he actually adds in the thickness of the circles or invisible crystalline spheres. Finally, Copernican heliocentricity arrived. With the Sun at the center of the universe, the Moon is relegated to a satellite of the Earth, and astronomers have only 6 visible planets to contend with. A few decades after Copernicus, Kepler is the first modern thinker to seriously wrestle with the new astronomy. Think of the largest sphere on the left to be invisible, but set within its equator is the planet Saturn. The invisible crystalline sphere carrying Saturn is tangent to the 8 vertices of the cube. Within the cube, tangent to each cube's face, is the invisible crystalline sphere for Jupiter. Just as there are 5 spaces between 6 chairs, Kepler spaces apart the invisible crystalline spheres for the 6 planets using the 5 Platonic solids. This does a fair job of accounting for planetary positions using the distances of Copernicus. The glaring exception was the distance for Saturn, which Kepler ascribed to errors in Copernican data. After all, it was so far away, what could we really know about it? But there was a small sleight of hand with the innermost calculation too, the octahedron that separated Mercury and Venus. For all the spacers, Kepler used the outermost or circumsphere and the innermost or insphere. As mentioned before, the circumsphere passes through all the vertices or corners. The insphere touches each facial plane in the center. I've not shown the facial planes here, the square for the cube, and the equilateral triangle for the octahedron. There is here, however, a third sphere that every regular polyhedron defines. The midsphere passes through the midpoint of every edge. So, to space the gap between Mercury and Venus, he uses the circumsphere and the midsphere of the octahedron. This became the seed point for all of Kepler's later work. He presented his conception of creation in a short book called The Cosmographic Mystery in 1596, at a time when he was still in his mid-20s. Long ago in a history of science class, the professor mentioned that Kepler had created another perfect solid, one beyond the then-known 5 Platonic solids. This led me to ask if Kepler was trying to predict the existence of a 7th planet. Dr. Westman simply said no, but I let this thought brew in my mind. Kepler actually created 2 new regular polyhedra, both with pentagrams as faces. The solid that the professor was referring to was the figure in the middle. Kepler called it the hedgehog, but we know it as the small stellated dodecahedron. After 8 years of struggle, Kepler abandoned the shackles of perfect circles to come up with what is known as his first law, that the planets have elliptical paths, where the Sun is at one of the 2 foci. This diagram is extremely exaggerated, but it is an attempt to show some of the variables that he had to deal with. The orbital planes of the 2 planets, Earth inside and Mars outside, are slightly different. He didn't know the exact shape of either orbit, and the Earth Observatory has a 23-degree inclination to its own orbital plane. Kepler's third law is that the square of any planet's year or period is proportional to the cube of its average radius from the Sun. I'll comment about this second discovery in a moment, but I want to mention that even at the end of his life, when he'd blown holes in the Copernican data for planetary distance and had seemingly disproved his cosmographic mystery, the thing he was most proud of was that same cosmographic mystery. Now, about Kepler's third law, that the square of a planet's period is directly proportional to the cube of its average orbital radius. When 2 variables are directly proportional, as one quantity, like a radius, gets larger, the other quantity, like period, also gets larger. This suggests that the further a planetary body is away from the Sun, the longer it takes for that planet to go around the Sun. So the next planet out from us, Mars, takes nearly 2 years to orbit. Jupiter, about 12 years. Saturn, roughly 30 years, and so on. Shut your eyes for a moment. I'll tell you when to open them. Galaxies were long thought to obey this law too. The further a star system was from the galactic center, the longer it will take to complete one circuit. Then, 3 decades ago, astronomers discovered several types of galaxy that were not obeying Kepler's third law. The most extreme of these exceptions show a handful of galaxies, with stars being propelled like dust, sitting on a record upon a revolving turntable. The outermost stars were turning at the same angular rate as the innermost. So if I say some things that sound extremely difficult to accept, bear with me, because I may have it together just as well as any astrophysicist. How well do they have it together? All the stars, galaxies, black holes, and planets only make up 3% of the universe's mass profile. Interstellar dust makes up 13% of that profile. About 83% of the universe's total mass profile must be composed of dark matter to explain the gravitational behavior of aberrant galaxies. This dark matter shepherds mass but has no neutrons or protons. It's something that gravitationally interacts, yet no one knows what it really is. In reality, then, astrophysics can explain very little of what's going on. One of my problems with this is that they think that dark matter is something happening out there in other galaxies, not here where all their ideas seem to be locked down. Open your eyes. This is a map designed for a hollow Earth model that's included in the book Etidorpa, first published in 1895. The title of this book can be remembered by spelling Aphrodite backward. The book can be read online. As mentioned previously, for attempting to publish some secrets, the main character is sentenced to exile in another world. The care of our exile is entrusted to a strange humanoid that can see, but has no eyes. After entering some Kentucky caves, K on the map, they make a long subterranean journey that leads to an underground cliff at O. They jump off the cliff, and rather than crashing into the opposite side of the Earth, they oscillate back and forth over the innermost dashed line. The oscillation is damped by some atmospheric effects, so that eventually they come to rest at the endmost dashed line, a line referred to by our eyeless guide as a sphere of energy or gravity. At this location, mass is weightless. There are 3 spheres here which affect the mass of solids. The outer Earth shell, which is the outermost solid circle, the inner Earth shell, which is the inmost solid circle at 800 miles below the Earth's surface, and the sphere of energy or rest, which is the inmost dashed line. There are 3 more spheres that affect atmospheric pressure, but 2 coincide with spheres already described. The outermost dashed line is said to be the outer bound of the atmosphere, about 200 miles above the Earth's surface. The atmosphere increases in density until a point about 10 miles below the Earth's surface. On the scale map, 10 miles below the Earth's surface is nothing, so we'll say that the second sphere of the atmospheric force coincides with the Earth's outer shell. In fact, geometric arguments that will shortly arise strongly suggest that the 10-mile depth of maximum atmospheric pressure must coincide with whatever controls mass near the outer surface of the Earth. As we continue inward, the atmospheric pressure starts decreasing, going to 0 by the time we reach the sphere of energy, rest, or gravity. The energy sphere is then doing 2 things. It makes solid mass weightless, and it repels gases. Once again, 2 spheres coinciding. In the book, there is no geometric explanation for these spheres, nor do I think this model is taken from a hidden geometry, because the sphere of energy is set at 700 miles below the Earth's surface in the book, but it needs to be at 575 miles below the Earth's surface, had it come from a hidden geometry. The geometry of the icosahedron on the left will fit the inner and outer Earth shell perfectly, but the sphere of energy on the previous map needs to be placed at 575 miles below the Earth's surface to match the midsphere of the icosahedron. On the right, the geometry of the dodecahedron is an excellent match for the atmosphere, but once again, the atmospheric repulsion properties for the sphere of energy need to be placed at 575 miles below the Earth's surface, not 700. For the geometry to thoroughly mesh, the circumsphere of the Earth's shell icosahedron has to align exactly with the midsphere of the dodecahedron at 10 miles below the Earth's surface. This may be the source of the Conrad discontinuity, a barrier that refracts seismic waves. The icosahedron on the left, with its 20 faces and 12 vertices, is the reciprocal of the dodecahedron on the right, with its 12 faces and 20 vertices. Both show the same ratio for circumsphere to insphere. What is happening with the midspheres, however, makes fiction look sort of ordinary. The mysterious mathematical properties of the midspheres for reciprocal solids becomes critical to much of this presentation. Think, the circum, mid, and inspheres of the dodecahedron align with the circum, mid, and inspheres of the icosahedron in such a way as to reduce 6 spheres to a total of 4. 6 to 4. This then might be the geometry of the Earth. Note that when we align the circumsphere of the icosahedron at the right with the midsphere of the dodecahedron on the left, the midsphere of the icosahedron aligns exactly with the insphere of the dodecahedron. The midsphere on the right is what I will repeatedly refer to as the sphere of energy. Switch the solids. Now we have a design for a different planet. But now, as we align the circumsphere of the dodecahedron on the right with the midsphere of the icosahedron on the left, the midsphere of the dodecahedron on the right will align exactly with the insphere of the icosahedron on the left. This will continue to happen each time we talk about reciprocal solids. This is the second, totally different manner in which the 3 spheres of the icosahedron align with the 3 spheres of the dodecahedron, reducing a total of 6 spheres to 4. 6 to 4. Twice. There are similarity pairs for rotation among the planets. Mercury and Venus find it very difficult to rotate once during their respective years. Earth and Mars rotate once in about 24 hours. Jupiter and Saturn in about 10. And Uranus and Neptune in about 16 hours. I believe that the structures you're seeing are also paired, accounting for the rotational similarities. The math here says that the geometric solid that controls the atmospheric forces will always enable its midsphere and insphere to align with the circumsphere and midsphere of the reciprocal solid describing the planetary shell. The sphere of energy for the Earth on the left is deeper than the sphere of energy on the right. Planet Earth is denser than Mars. From now on, given a pair of planets based on reciprocal solids, the denser planet will be that which has a deeper sphere of energy. As in the discussion of Eta Dorpa, this sphere of energy would attract solid mass and repel gases. To affirm the correlation between Eta Dorpa's apparently icosahedral Earth model, I introduce a Russian map that was floated in a science journal called Chemistry and Life in 1973. They actually borrowed the best part of it from Ivan Sanderson, who in 1972 studied places like the Bermuda Triangle and the Devil's Sea, and found that they were equidistant from one another, and was led to the underlying icosahedral map, the one based simply on triangles. The Russians' overlay of the dodecahedron does seem to map out other anomalies, but they're not consistent categories. In some intersections you have havens of unique plant or animal species, in other locations hyperseismicity. Whether it's Earth or Mars, the symmetries found therein are best embodied in the spherical icosahedron. The sphere on the right, excluding the white arcs, resembles the map of the Russian researchers. The white arcs actually represent a spherical rhombic triicontahedron. The image of a spherical icosahedron is not hard to grasp. A light placed at the center of an icosahedron would produce the shadowy outer edges of the equilateral triangles on a surrounding circumsphere. Including all the altitudes from each vertex would get us 6 smaller triangles within each equilateral triangle. Icosa, meaning 20. 20 times 6 gives us 120 smaller triangles. 60 are congruent, 60 are mirror images. With the use again of a central light within a dodecahedron, the image of a spherical dodecahedron can be produced on a surrounding circumsphere using shadows. If the regular pentagonal faces had all the altitudes drawn in at each vertex, each pentagon would contain 10 smaller triangles. Dodec, meaning 12. 12 times 10 produces 120 smaller triangles. Again. Place a central light within the rhombic triicontahedron. The shadowy image projected on a surrounding screen would be a spherical rhombic triicontahedron. Draw in the diagonals, and you get 4 smaller triangles. Triconta, 30, times 4, gives us 120 smaller triangles. Why do we get 120 triangles each time? Because it's the same resulting figure each time. We call it a spherical icosahedron out of convention, but it might just as well be called a spherical dodecahedron or a spherical rhombic triicontahedron. If you look at this spherical icosahedron carefully, you'll see an icosahedron in green, a dodecahedron in blue, and a rhombic triicontahedron in tan. Plato himself felt that the Earth was a patchwork of 120 triangles. Now I want to glance at a second pair of reciprocal solids. The cube on the left has 6 faces and 8 vertices. Its reciprocal, the octahedron, has 8 faces and 6 vertices. Note once again they both have the same ratios for the circumsphere to end sphere. But the midspheres once again differ, and once again in a baffling way. Both Mercury and Venus have trouble rotating once during their respective years. One of them rotates less than once during its year, the other rotates slightly more than once during its year. Once again, we're going to see 6 spheres becoming 4, and this in 2 different ways. Starting on the right-hand side of either figure, the circumsphere and the midsphere of the planet's shell coincide precisely with the midsphere and insphere of the atmosphere on the left. Compare the right-hand side of both figures. The sphere of energy, or midsphere, is deeper on the first design. Mercury is denser than Venus, so I assign the first drawing to Mercury and the second to Venus. While I'm showing you what I believe to be Mercury, the symmetries of either of the previous designs are embodied in the spherical octahedron. The spherical octahedron has the same naming problem as the spherical icosahedron. It can be looked at as a spherical cube in black, a spherical octahedron in orange, or a spherical rhombic dodecahedron in white. There are 4 concave regular polyhedra in addition to the 5 convex Platonic solids. The first and third of these was discovered by Kepler early in the 1600s. The second and fourth were discovered by Louis Poinsett in the mid-1700s. This second set of solids comes from a process called stellation. Start with the dodecahedron at the left. Extend its edges until they intersect, and you get the second figure, the small stellated dodecahedron. take any pentagram, like the green one on the second figure, and connect consecutive vertices. The planes now become pentagons, giving us the third figure, the great dodecahedron. Focus now on the outer edges of any pentagonal face. Extend those edges and we get the fourth figure, the great stellated dodecahedron. Now we have defined 3 of the 4 regular concave polyhedra. To get to the final regular star polyhedron, imagine extending the planes of the small white icosahedron. The planes intersect and re-intersect dozens of times, creating about 50 somewhat irregular polyhedra before we arrive at the great icosahedron. While this figure looks similar to the small stellated dodecahedron, which has pentagram faces, here the faces are all equilateral triangles. In examining the first pair of reciprocal concave polyhedra, note that once again the ratio of the circumsphere to the end sphere is the same. And the mid-spheres should once again leave us pondering, once again turning 6 spheres into 4 in 2 different ways. The next pair of planets beyond Earth and Mars are Jupiter and Saturn, both of which rotate in about 10 hours. The planet shell is still on the right side of each figure, but the planet shell is now shepherding frozen or near freezing gases. The figure on the left of either model might be thought of as a ring driver. The planet shell for the left-hand figure has a deeper sphere of energy than the figure to the right. Jupiter is denser than Saturn, so the model to the left could be Jupiter, and the one to the right could be Saturn, if we can account for any of the geometry in either planet.
There were strange features called spokes, patches of dust particles slightly raised above the rings. These caught the eye of one young graduate student.
I got involved in the study of the spokes, which were these ghostly features that were seen to come and go. And it just came to my head to just kind of categorize the pictures. Into one pile, I put all those images that seem to have a lot of spokes in them. Into another pile, I put those images that seem to have virtually no spokes at all. And I made an intermediate category. And of course, each image was tagged with a time. And I basically just did an analysis on the computer of this and found that the spokes actually weren't just sporadic, but in fact they came and they went with a certain period.
Carolyn Porco discovered that the spokes followed Saturn's magnetic field as it rotated with the planet.
I made my very first scientific discovery, and just knowing that I had found something that nobody else on the face of the planet knew at that time was just such an exhilarating experience.
In the short clip we just saw, the spokes sometimes extend all the way to the edge of the B-ring. The B-ring is the portion filled with the alternating gray and white ripples. The ratio on the left suggests that the circumradius of the great stellated dodecahedron extends outward nearly 3 planetary radii. The second ratio suggests that the spoke effect extends out to the edge of the B-ring at about 2 planetary radii. While any of the 4 solids might provide an electrostatic charging mechanism to raise dust particles above their plane of rotation, this one looks more promising to me. There's a pentagram above, near, and parallel to the ring plane here. There's also an inverted pentagram parallel to, near, and below the ring plane. In addition, 10 edges of the great stellated dodecahedron will pierce the green B-ring plane near its outer edge. Another possibility for the spoke creation comes from the small stellated dodecahedron and the great icosahedron. While we still have 2 inverted pentagrams parallel to the ring plane, they're more distant here, and no edges would pierce the green B ring at all. The circumsphere for either of these figures will encompass the B ring, but just barely. The circumradius of the great stellated dodecahedron would end just beyond the start of the G ring. Everything outside the G ring really doesn't qualify as a ring because the material beyond is not a thin, flat disk. It spews outward into space in a wedge formation. However, in showing you this graphic, I don't want to leave you with a misleading impression. I'm not saying that the circumradius of the outer solid is responsible for the extent of the ring disk. That hypothesis would fall short in part when examining the ring system of the other three outer planets. When a single spherical icosahedron is colorized for the planes of the corresponding solids here, it's the first instance where the spherical icosahedron is fully colorized. Note an overlap effect of the two solids at the 30 spherical rhombi. Intuitively, I would suggest that the full utilization of the icosahedral symmetry has something to do with why the gaseous planets are the fastest planets rotationally speaking. Traditionalists may cling to Newton's first law and suggest there is no need for a theory of planetary rotation, but true knowledge of how gravity operates right here may involve dark matter and rotational speed. I've reoriented the spherical model for the Jupiter-Saturn symmetries. To its right was the spherical model for the Earth-Mars symmetries. In the model on the right, 30 rhombi are left unpainted. Before we go to the next slide, note the potential for hexagonal symmetries. This is a hexagonal weather pattern at one of Saturn's poles. There is an obvious type of position for this hexagonal symmetry to occur on the great icosahedron. I've placed a yellow pole through the solid at this point. This is how the invisible structure might be oriented to define Saturn's planetary shell. In all the foregoing arguments, I could have used the two remaining solids to seek an explanation for Saturn's B ring and the hexagon at the poles. But I didn't because the proximity for the great stellated dodecahedron's pentagonal planes, parallel to the B ring disk, may provide the best explanation for the spokes therein. You may have forgotten what all this verbal gymnastics has been about. Using the great stellated dodecahedron and its reciprocal, the great icosahedron, we've spent considerable time on Saturn, potentially the model at the right. Comparing the right side of each figure, the sphere of energy is deeper for the figure on the left. Jupiter is denser than Saturn, suggesting that Jupiter's invisible design is on the left and Saturn's is on the right. The remaining pair of concave reciprocal polyhedra are the small stellated dodecahedron and the great dodecahedron. Note once again that the ratio of the insphere to the circumsphere is the same for both, but the midspheres differ. The midsphere for the object on the left has to pass through the edge midpoints of a pentagram. The midsphere for the object on the right has to pass through the midpoints of a pentagon. A few minutes ago I tried to show you other possibilities for the ring driver of Saturn. I did not include the figure on the right, the great dodecahedron, because its midsphere is relatively close to the circumsphere. The circumsphere in that case would be incapable of extending as far as the B ring. As we seek a geometry for Uranus and Neptune, there are two designs that remain. I consider these two planets to be a rotational pair. One of the planets rotates in 16 hours, the other in 17. Compare the right side of each figure. The planet shell on the left has a shallow, hardly visible midsphere or sphere of energy, when compared to the energy sphere of the other model. Uranus is less dense than Neptune. I therefore ascribe the figure on the left to Uranus, the other design to Neptune. Colorizing the spherical icosahedron on the right to match the parallel planes of the small stellated dodecahedron leaves a considerable amount of the sphere inactive, as shown by the white in the great circles. Again, colorizing the spherical icosahedron on the right to match the parallel planes of the great dodecahedron leads to parts of the sphere being unpainted or inactive. But when this spherical model is combined with the previous model, we will once again get an overlap at the 30 rhombi. What we've seen so far using the geometry of reciprocal solids and planetary rotational pairs, is a promenade of couples, conjugal pairs as it were, strolling around the sun in their ever-obedient elliptical paths. When we looked at the terrestrial planets, I belabored the 6-8 relationship of the cube and octahedron. Was it 6 faces and 8 vertices, or was it 8 faces and 6 vertices? I also stressed the 12-20 relationship between the icosahedron and dodecahedron. The tetrahedron is the oddball. It has 4 faces and 4 vertices. You switch the 4 and 4, and what do you get? Does this mean the tetrahedron has no reciprocal? Not really. It means the tetrahedron is its own reciprocal. Let's imagine the small orange tetrahedron on the right forming the shell of a planet. Place the second brown tetrahedron in the position for an atmosphere. The midsphere for the atmosphere will perfectly align with the planet's surface, while the insphere of the atmosphere aligns perfectly with the planet's sphere of energy. Well, where is this androgynous planet? I don't know, but I'll say this much. It's terrestrial because it's formed from a regular convex polyhedron, and it probably rotates slowly because, like Mercury and Venus, it lacks icosahedral symmetry. Some have suggested that Nibiru is on a strange elongated path with a 3,600-year cycle, and the analogy of having no planet to promenade around with is more than intriguing. Or perhaps we should reinstate Pluto. All of this leaves us with more questions than answers, but I need to try to wrap this up. Colorizing the great circles of the spherical tetrahedron for this possible planet actually leaves the outline of a spherical cube in white. Yet the spherical tetrahedron generally has different symmetries than the spherical cube, also known as the spherical octahedron. I'm not going to show you the Chilbolton crop circle of 2001. Though you can easily Google it, and you'll see that it appears to be a line-for-line response to the 1974 radio transmission sent from Arecibo, Puerto Rico. In 74, scientists sent a message to a large cluster of stars 21,000 light-years away. In an attempt to contact other intelligent species, they developed a message based on prime numbers and binary language that would tell an intelligent civilization something about Earthlings. The line on the Arecibo message that we are considering here is represented in black. The 3x3 block at the right stands for the Sun. The 2 1x1 blocks that follow represent Mercury and Venus. The third 1x1 block is raised to designate that we live on the third rock from the Sun, and in the original message they posed a stick figure human over it. The crop circle response was interesting. Not so much because the stick figure ET was so different than us, but that it stood over 3 raised planets, as if to say they live on the outside of the 3rd and 4th planets and inside the 5th. Nor is it too surprising that they might have 9 planets also, suggesting perhaps that when stars have planets, they are designed around the 9 regular polyhedra. In this photo we see Nassim Haramein venturing an explanation for an ancient Mayan artifact. Here he identifies several UFOs manifesting over a planet, presumably Earth, with a very thick atmosphere. I think he might as well just be looking at a hollow Earth from wherein UFOs might originate. Are we heirs to an ancient and forgotten wisdom? Is there fruit in the Greek concept of planetary motion by invisible crystalline spheres? Are there fields of dark matter just below our feet? I leave these questions for another generation to ask. At this point, I want to leave the geometry of the planets and talk about the origin of this thesis. While the popular notion is that all ideas have their origin in the brain, I'm going to make an argument that some ideas come from outside the brain. How else can 2 people living a century apart come up with the same set of ideas? Back in the fall of 1974, I was a struggling political science major at UCLA. I had no interest in science or engineering and therefore couldn't come up with a psychological reason for why I dream about technology. Yet, dream I had. In this dream, a door cracks open, and an extended arm hands me a diamond-shaped piece of glass, a faceted octahedron. I turn in this dream to look out a window and see a spinning sphere with a metal tail skirting across the sky. Bear with me through one more dream. This about 1 year later when I was well into my political science studies. I'm asleep, but I see a ball of sunlight being formed by two streams of light, and under it is written the algebraic expression 1 EEEMM equals. The next evening, I found a book with a lot of E's and M's in it, and I checked it out of my local public library. Quantum Electronics by John R. Pierce. There in the foreword, the author made mention of some long-forgotten story writer named Fitz James O'Brien and his story The Diamond Lens, wherein the inventor builds a powerful microscope that can see to the very heart of matter. While this first story reflects the darkness of a tale written in the time of Poe, a second of O'Brien's shorts sparkles with playfulness and wonder, a piece posthumously published in Harper's sometime in 1865, a work called How I Overcame My Gravity. Therein, O'Brien endeavored to describe how to fabricate a spherical launch vehicle with an iron tail. If it rotated fast enough, it became weightless. It could then be catapulted considerable distances. But there, at the start of this story, lay the following passage. For a long time, I turned my attention to solving the problem of aerial locomotion. I fancy even now I hit the white when I enunciated my grand principle of progression by means of atmospheric inclined planes. And at the time, I made a model of a machine which illustrated my theory fairly well. It took me a while to get to progression by means of atmospheric inclined planes. The first step was to look up and find Kepler's hedgehog and its 3 stellated companions. The second step was to resurrect Kepler's Mysterium Cosmographicum. But now I had 9 planets and 9 solids and not 9 planets and 8 spacers. And the geometric ratios didn't come close to the planetary distances. After I buried that idea, I found something at the bookstore called The Hollow Earth. That book showed an 800-mile thick Earth shell, and I knew both the dodeca and the icosahedrons, circum and inspheres, could account for this girth. I showed this curiosity to my dad, and he just said, "Go downstairs and get a pink paperback off my bookshelf." That book was Edda Dorpa. How is it two people a century apart come up with a diamond lens, a flying sphere with a tail, and a plausible hypothesis called progression by means of atmospheric inclined planes? I would suggest that there are archetypes of technology, forms, or ideas that exist on their own in a pure realm of being. Occasionally, one of us stumbles upon it, and we actually think twice about it. So, do some ideas come from outside our brains? You decide.